Hi everyone, I'm Pranay, and I'm from GCSR, and I'm doing my master's in public health epidemiology, and I'm based in Vellore. Um, I'll quickly introduce the Global Consortium for Stroke Rehabilitation to each one of you. This was founded by our. I'll introduce them later, but just to explain our vision as a consortium, it is to create a world of. There are five things that we focus on. One is relevance, high quality, patient centric, accessible and affordable stroke rehabilitation services, and we focus on low resource settings. This webinar aligns with our vision. It is to co-create a technology and implement it into or contextualize it into low resource settings. And we're so grateful to have Anshul here. He's Anshul Bharadwaj. He's actually a journalist who works with India Today Group, and he's a stroke survivor. It'll be wonderful to hear from him today. To start off, I would like to welcome Sivakumar sir. He's a professor and head of the Department of Bioengineering here at CMC Vellore, and he has a PhD degree in bioengineering from the Arizona State University. Um, he was a researcher and a postdoctoral researcher with Imperial College London, and he is a researcher at Technalia Research and Innovation Spain. So he joined CMC Vellore in 2014, and he has been with the department since. Um, it'll be wonderful to hear his insights into this webinar, and I invite him to take over and speak.
Unmute. Am I
We
audible?
can hear. Yes, sir. We can hear you. Thank you.
Yes. Okay. All right. Thank you, Pranay, and thank you for the GCSR team for the invitation. Um, okay. All right. Good evening, everyone, or good morning for people joining from across the globe. Yeah. So the title for today's talk, when John contacted me and he said they would like me to talk about some of the work that we're doing on what he termed as accessible technology, I said, yes, sure. I'm happy to talk about what we do. And yeah, it's changing. Okay. So the title for the talk, as I said, it's accessible technology for stroke rehab in low resource setting. So essentially what we're going to be looking at are therapy tools, tools that we use for implementing rehab for our stroke patients. And we are looking at, we're talking about accessible technology. That means technology that has minimal barriers for procurement and use by a wide range of people, clinicians and patients in different settings. And in particular, we're talking about in low resource settings, which means essentially places that have limited means for doing this, right? If that is all we are going to talk about, therapy tools, minimum barrier for procurement use in places with limited means, then in fact, we already have these technologies. In fact, we've been using it all along. And practicing clinicians are quite familiar with all of these, right? Because these are tools that we already use. And you go to any rehab clinic, they should have tools like this, which they actually use for implementing different forms of therapy. And these are excellent tools because they are fairly cheap, easy to maintain, easy to repair. If it completely breaks down, you replace it with a new one. Right? So it has a lot of nice things to offer. And in fact, it fits the title, Accessible Technology for Stroke Rehab in Low Resource Settings. But the only issue is these technologies, we might not think these are technologies, but they are technologies. They are technology nevertheless. The only problem is they have severe shortcomings, and they do not actually give us the benefits that we actually seek from tools that we want to employ in neuro rehab. So it's not appropriate to talk about only accessibility without talking about benefits. And I would say that accessibility of technology is relevant only in the context of benefits. So with that background, I move on to the next slide. And before we move on, I've introduced two terms, accessibility and benefit. Let me just briefly talk about what these are, what are the benefits we are talking about when we're talking about benefits from technology and what constitutes accessibility. Let me start with benefits. If you're talking about benefits, there can be multiple benefits or different types of benefits we might want from technologies for neuro rehab. One could be an outcome benefit. So we might say we want our technology to have superior outcomes if I use the tool versus if I don't use the tool. So that means the tool gives me good clinical outcomes when I use it. There could be process benefits. The tool could enable you to make therapy much simpler and more efficient, the way you're implementing and delivering therapy to your patient. That's a possibility. Uh, the tool could enable a clinic to make better use of their skilled labor, the clinicians and the nurses and people like that, if the tool was available. A third could be it could enable us to make difficult things possible. That could be a benefit that you might get from the tool, and there are many others that we could list. So these are the benefits. Ideally, these are some of the benefits we would want from our tool if you're going to be employing it for neuro rehab. And if you're talking about accessibility, accessibility again is got multiple facets. Accessibility could include things like is the technology affordable, and the services offered with this technology, are they affordable? Another thing could be, does it adapt to different contexts? For example, if you're talking about India, does it support different languages and cultural backgrounds? Other thing could be, is it portable and compact? Or is it so big that it can only sit in a quaternary hospital in a big city? Or can it go into a patient's home? So portability and compactness also determine accessibility. Another thing could be, what are the resource requirements? Does the device have to be always powered from the mains? Does it require a constant presence of an internet connection? And all that. And all of these factors that in the technology will determine accessibility. So we are essentially talking about fairly complex constructs here in terms of benefits and accessibility. And all of us will agree that what we really want is not just highly accessible technology. What we want is technology that is both highly accessible and it also has high benefits. Right? And which is what I'm terming as value, which is essentially the product of accessibility and benefit. And what we want from our technology is high access and high benefit. That means we are looking at high value technology. Right? So with that, with value, which is the product of access and benefit, that's how I'm defining it for the purpose of this talk. We can, with that as a metric, we can now ask, well, how much value do conventional tools provide us? And in fact, we can argue that these actually have quite low value. They have high access, but they don't offer us a lot of benefits that we would ideally like. They don't do any automatic tracking of movements. They don't provide any feedback to patients when they're engaging with them, and which essentially leads to poor engagement during therapy, poor adherence and dosage, which then translates to poor outcomes. So we can safely say that the problem with our conventional tools is that even though they're highly accessible, they actually provide very little value, or they don't give us the value that we actually seek, right? And advanced technology, which is actually, I'm sure, what all of us had in mind when you read the title, when it said accessible technology, you were essentially thinking of stuff like this, right? Robots, sensor-based systems, and computer vision systems. These can actually help in improving benefits. And the way they can do that is through some sort of automation of the therapy process. They can give interesting and engaging feedback. They can make remote therapy possible. They can measure a lot of data. That means maybe we can do more quantitative, we can look at patient response and things like that more quantitatively. And if you have a robot, we can also assist people to move, which could be encouraging for them, which could be an encouraging factor for them to really engage in therapy. So these are all benefits that these advanced technologies can offer us, right? Now the question is, okay, I buy the argument that these technologies offer benefits. Now, do they really add value? Now, if you look at work in the last 30 years, at least in rehab robotics, there's been a lot of work. And if you look at the status quo, we've unfortunately not been able to show a lot of efficacy with these devices, especially with robotic devices. And a lot of the focus has been on in-clinic solutions. That means most of these devices stay in a clinic, which patients need to come to access and use these technologies, which is also a problem, because the demand for neuro rehab is quite high worldwide, and in fact, especially in countries like India. And the only way we're going to solve this problem at scale is not in the hospital, but it's in the community or in the patient's home. So the solutions sitting in the hospital has not really helped our cause. We can design the technology, but it's unclear how it fits into somebody's regular clinical practice. Am I still audible?
We can hear you now, sir, but we can't
Yeah.
see.
Is
Yeah,
it,
I
can
can
you
see your
see
screen
now?
now.
Sorry, my internet can be
Yeah,
choppy
yeah.
at times.
No
I
problem.
apologize.
No problem.
Right.
There's
So
no problem.
I said earlier that these devices can collect a lot of data, but frankly, we don't know what to do with this data. We've not been very successful at deriving useful information from this data. And last, in fact, this should be the first point. Most of our technologies are too complex and too expensive. Right? So with this status quo, I would argue that our current advanced technologies also have not managed to provide us much value. They've added some benefit, but access to these remain significantly poor, which essentially brings down the total value that these devices add. Then the question is, well, if that is the case, what do we do? We like the benefits that these things offer. Now, how do we go about designing a technology that can give us both high benefit and high access? Right? And when I usually talk about this stuff, I generally propose three things. These are philosophies that we follow in my group as well when we think about designing tools for neuro rehab. The first thing that we definitely follow is try to keep things as simple as possible, but not simplistic. You need to get rid of unnecessary things in your technology without compromising on the benefits that the technology can offer. So that would be the first thing. And this also addresses my previous point on technology being too complex. And the technologies that we design have to enable and not constrain the clinician. For example, the great thing about rubber bands and wooden blocks and things like that that are used in the clinic is clinicians can do a lot of different, very creative things with those things because they're very robust and they don't necessarily constrain you from doing things. So when we design technology, we need to essentially allow or make them feature rich so that it allows the clinicians to do a lot of things with the technology. You simply cannot have a 30 lakh robot that sits in your clinic and it only does one thing. That definitely does not help. And lastly, again, another thing that we must focus on is devices should not just be designed for the clinic. Of course, there are devices that should only be designed for the clinic. If you're talking about gait and big robots where safety is an issue and things like that. But if you're talking about upper limb and relatively simple joints and movements, then the technology we design we need to think of uh, trying to get the technology out of the clinic. It has to work outside as well. And these are three general principles that we follow in most of the things that we do in the lab, in my group. And we are a research group at the Christian Medical College, Vellore, in the Department of Bioengineering, as Pranay pointed out. We are the Biological Learning and Rehabilitation Group. We work at the interface of engineering, movement science, and neuro rehab. And we focus on two things. First, to simplify and translate technology, we ideally want everything that we develop in the lab to go out and get into society. So translation is a big part of the work that we do. And the second aspect is looking at how do we quantify movements. But this is not something I'm going to talk about in this talk. I'm only going to be focusing on our work on simple technology for neuro rehab. And in this context, I'll talk about 6 different devices that we've worked on or currently working on. The first 5 are devices that we are currently developing or have developed in the lab. The last one is a device that I developed when I was a postdoc in Imperial, and we did some testing of evaluation of this device at CMC after I moved here. Because I think these are examples of technologies which offer benefit and have high accessibility, at least in our opinion. Right? I'll start with the first device, which is called Pluto. Uh, it stands for Plug and Train Robot for Hand Neuro Rehabilitation. This is one of the first devices we started working on. This is work done by my former PhD student Arvind in collaboration with Professor Sujata Srinivasan from IIT Madras. Uh, Pluto is a compact, portable, modular robot for training hand functions, and it's essentially inspired by Kitchen Blender. That's why I have a picture of Kitchen Blender and blades here. So the robot has a single degree of freedom, a single motor, and depending on what you want to train, you simply attach a mechanical handle that's designed to train that function, just like how you'd use a blender. I'm not going to go into the details of the robot. Let me play the video of the last version of the robot, or at least the lab version of the robot. Uh, so that's the robot with the computer. The entire robot comes in a hard case, and that's essentially the robot. So it has, sorry, yeah. Yeah. The motor, the electronics, everything sits inside that. Sorry. Everything sits inside this box. It can sit on a trolley or on a table. So you can move it around wherever you want. And there is a shaft that sticks out, and you can attach whatever handle you want, an appropriately designed handle to train that specific function. You put it in, and then there is a lock. You lock it in, and then you're ready to go. Right? So there are 4 different handles that we've designed. 2 for the wrist, 1 for forearm, 1 for gross hand opening and closing. These are more abstract movements. And we also have functionally shaped handles for training more functionally relevant movements. There is sensors in the device that can measure your movement and maybe the forces that you're applying. And of course, all of this is gamified. Just the presence of the robot itself is not enough to make therapy interesting. So your movements are then mapped to some game to essentially keep patients engaged. And because the robot has a motor, if you have a relatively severely impaired patient who does not have a lot of movement, the robot would be able to assist them while they are training, which can be an encouraging factor for them to at least attempt and engage in therapy. Right? So that's the current, the last version of the robot. And as you saw, you could move the robot around easily. It's quite lightweight. It can be placed on a table, which means now, if this particular device does not have to go to the patient the patient does not always have to come to the robot. The robot can go to the patient in a hospital. For example, this is somebody using the robot by the bedside in the neurology ward at CMC Vellore and Ranipet. So essentially, I'm arguing that this increases access because the patient, let's say, if he or she is unable to come to the ward, the therapy ward, then the robot can be taken to them so that they can still do therapy on the bedside. Right? So that was in-clinic use of the device. And I kept emphasizing that things have to go home, and that's something we did recently. So we did a case series where 5 patients used the device at home, and what we found was when the device is set up at home, therapy time essentially doubles. People were able to do twice as much therapy per day compared to if they accessed the robot in an outpatient basis in the hospital. And a real success story for us in terms of using the device in a low resource setting was one of the participants was a young chap from Javadi Hills, which is a tribal village about 100 kilometers southwest of the hospital. So this is a video of us taking the device to the person's home. And there are also clips of the person using the device. Again, this is a good example of a low resource setting, intermittent electricity, intermittent mobile connectivity. And once the device was set up, the participant was able to use the device with the help of his family member for about 6 weeks. Right? So this was actually, a very positive thing for us because we knew that the relatively simple design, simple and robust design, has essentially made it possible for us to use this device in a low resource setting like the Javadi Hills. And another thing that we did, well, Javadi Hills is an example of a low resource setting. Another thing that we did was to ask, well, what about even more difficult settings? And this was essentially a tribal area in Gudalur. So we did some preliminary testing with the Gudalur Ashwini Hospital, which is a Adivasi hospital. And these are pictures of us having taken the devices to the homes of the tribals there. And this was a very good learning experience for us because we realized that the current version of the device is actually not suitable for a place like Gudalur if it is to be used in the homes of tribals in Gudalur. So there is still some more simplification, other factors that we need to consider. For example, you can't rely on main supply. You need to have a battery operated device and maybe solar charging. And in fact, some of the handles we had designed were actually quite big for the tribals because they're generally their sizes are generally smaller. So So although we find that Pluto is usable in a low resource setting, if you're talking about a more severely resource constrained setting, there are still some more features and engineering improvements that need to be added before it can go to a resource setting like in Google. So that's all I wanted to say about the hand robot. Next one is a device for the arm. Now, there have been lots of ARM devices that people have developed, some end effectors to multi degrees of freedom end effectors to multi degree of freedom exoskeletons. Uh, and if you look at stroke, right, one of the biggest problems in shoulder elbow movement after stroke turns out to be working against difficulty against working against gravity. So there has been some recent work where they show that if you can provide gravity support, stroke patients can actually already do a lot of movements, and that might be uh, uh, good for essentially addressing reaching problems. So based on this work, we then started asking, well, can we then design uh, an end effector robot, because end effector robots tend to be simpler and they can be easily used for both the left and the right arm, that can enable 3D movements. We should be able to allow patients to train in a plane and at the same time be able to provide gravity support, because gravity is the biggest problem, or at least one of the biggest problems for shoulder elbow movements in patients with stroke. So what we ended up designing was then again a robotic device with a single motor, a picture of which is I'm showing here. That's the device attached to a person's forearm. There is one motor in the device which essentially provides gravity support, support against gravity, and there are other sensors here which will essentially, or other degrees of freedom here, which will allow the person to move in a plane, and all of it can be measured and given as feedback. Right? I'm going to play a video of the current version of the device. MARS, which stands for motorized arm support. That's the current device. The motor sits in here, and we can essentially move the device in this axis by actuating the motor. This person's now has donned the device and essentially showing the different movements that are possible in the plane, and we can change that plane as well. That's what allows us to do 3D movements. We essentially enable three types of movements: medial lateral, anterior posterior, and a mix of medial lateral and anterior posterior. And here, this video shows an assessment of how much the person can move in the medial lateral direction. This is essentially a game that they're playing, focusing on medial lateral movements. The next one will be again a game where we are looking at anterior posterior movements. The focus in the previous one, the focus was on shoulder movements. This is primarily on the elbow, and a mix of these. And we have games for looking at a mix of these two as well. So that's Mars. That's still this device that is under evaluation right now. We are just about to start a usability study with this device, and this also is work with Professor Sujata from IIT Madras, and again our former PhD student Prem essentially did his PhD on developing this device. So that's another device, relatively simple device compared to existing arm robots for shoulder and elbow training for stroke. The third device that I want to talk about, this is a device that is very early in its development, so we don't really have a full-blown prototype as yet. But I still wanted to talk about this because we believe that there are some nice features that we're bringing in. Now, if you look at ankle issues after stroke, right? Patients normally have problems with dorsiflexion, so they have poor it should be foot clearance, sorry, not poor foot. They usually have poor foot clearance because of weak dorsiflexes, and they also have weak plantar flexors, which actually leads to poor push-off. So in fact, both dorsiflexion and plantar flexion are a problem to be able to walk safely and efficiently. Right? And if you look at foot clearance, then you're essentially looking at strengthening the dorsiflexors just enough so that the person's able to lift the foot sufficiently to do ground clearance. And if you're talking about push-off, of course, you need good plantar flexors, but along with the plantar flexors of the ankle, the toes actually play an important role in being able to push off fully. And in fact, toes also play an important role in static and dynamic balance. And if you look at the current literature, almost all ankle robots will have only focused on the ankle joint. There are essentially no robotic devices right now that have looked at training the toe as well, which we think is a problem. What we hypothesize is if you train both the ankle and the toe, the outcomes are likely to be better than if you only focused on ankle training. So not having any device for toe training the toes is a problem. And we also think you don't need to assist movements in all directions. For example, if you're focusing on the ankle, you don't have to assist both in plantar flexion and dorsiflexion. It might be it's good to assist in one and maybe resist in the other direction. And given that these are lacking currently in almost all ankle robots that exist in the literature, so we then decided to design a new robot, which we're calling the Autobot, which is ankle and toe rehabilitation robot, which will address some of these. So this is a device that will allow both ankle and toe dorsi and plantar flexion. It will assist dorsiflexion, but will resist plantar flexion to strengthen the plantar flexors. Right? It's a device that is designed to be used in sitting, standing, and lying positions. And again, it's something we want to make that will be compact and portable so that this can be taken home as well. This is the 3D model of the current device. We have a mechanical structure of the device, at least part of it completed, which is what I'm showing here in these pictures. And it's got 2 degrees of freedom, one for the ankle and one for the toe. Right? So that's the ankle robot. I'm hoping maybe 6 months down the line, we will have a full prototype that's undergone some evaluation with patients. So that's another device which we think fits the bill of a high-value device for neuro rehab, focusing on ankle and toe function. So the first 3 that I've talked about are essentially robotic devices. Now I switch to non-robotic solutions because a robot is not always needed for rehab. If you have patients who are relatively high functioning, you don't really need a robot. A robot is an overkill there. And this device that I'm going to talk about is called Hypercube. This was work done by my former master student Rama. And the previous device again was Autobot was worked with Sujata from IIT Madras, and our current PhD student Neelakshi is working on the device. Now, this Hypercube, no, Pluto, when I talked about Pluto, it was a robot for training essentially gross hand functions. But if somebody already has some hand function, then and they're interested in more complex functions, more finer hand functions, then these are some of the tools that clinicians might employ to implement therapy for training those functions. Right? And Hypercube essentially makes a sensorized version of this, at least for a selected class of functions. So Hypercube is a cube-shaped object, as shown in this picture, which essentially packs multiple functionalities into a compact form factor. So we've tried to at least simulate different types of finer hand functions, hand grip control, key pinch, tripod grasp, and knob manipulation type tasks in the device so that we can provide enhanced feedback. Now, a cube and the approach that we've taken is a cube has 6 faces. And what we've tried to do is essentially put an interface on each of the 6 faces to be able to train different hand functions. That way you have one object that is able to then provide multiple solutions, focusing on adding a lot of features in the device. So these are some of the things that you can currently do with the device. You can measure and train gross grip. You can train pinch grasp as if you're picking up small objects. You can also train tripod grasps. There are different size knobs for training knob manipulation. Those are these 3 pictures. And there is also an interface for training individual finger movements. Let me play videos of the device being used by clinicians. So these are videos of patients using the device at CMC Ludhiana, where they did some preliminary testing of the device. So the device is again connected to a computer where your movements and your interactions are gamified. Okay, that's Hypercube, a device for training more finer hand functions. The next device that I want to talk about is actually a device that is based on a device that is very commonly used after stroke, which is the arm skateboard, which is called NOARC, and which essentially stands for Not Just an Arm Skateboard. And this is work done by my former master student, Sujit. So arm skateboards are commonly used early on after stroke, especially when somebody's flaccid and they can't work against gravity. You use the tabletop for providing gravity support and encourage them to essentially make movements at the shoulder and elbow on the tabletop. The skateboard is a great device. It's simple, it's easy to use, and anybody can use it. The only problem is uh, it does not provide any feedback, and it's not fun to use maybe after 2 minutes. And that's the biggest problem. Right? And we wanted to address this, and so we considered a lot of ways of doing this. And our final conclusion was, well, we need to try and not change the form factor of the skateboard as much as possible. That means don't put any electronics or anything on the skateboard, and still try and see if we can track the position of the skateboard. That way we can provide feedback, and therapy possibly becomes more engaging. And that's essentially what we wanted to do: track the position of the skateboard with minimal changes to the skateboard, and that essentially led to NUAC. And the way we do that is essentially by placing what look like QR codes on the skateboard. This is a 3D printed skateboard. So no electronics, is still a purely mechanical device with some stickers on it. And the position of these stickers are essentially tracked through a simple camera, a Raspberry Pi and a camera. And this is Sujit essentially demonstrating the device. So the camera is here, and then he's moving the skateboard, and the movement of the skateboard is tracked by the camera, and that's then converted to characters movement in a game. Right. So once after we built this device is currently being trialed in the Rehab Institute. This is a participant using the device for at the Rehab Institute using the device. And we've called it not just an arm skateboard because you can actually detach the handle and still be able to do 3D arm movements as well. That's why we are calling it not just an arm skateboard. So it can function as a skateboard, or it can also be used for doing 3D arm movements, essentially working against gravity. So that was the fifth device that I wanted to talk about. And the last device is essentially work that was done at Imperial College almost 15 years back. And this is Sitar. This is essentially an interactive general purpose tabletop with instrumented objects. A table is a common thing that is used in rehab clinics, right? So what we wanted to do was make the table more interesting, and that's essentially what we did. So this is a tabletop. We are calling it an interactive tabletop because the tabletop is formed by a TV and a glass plate on top. And if you touch the glass, we can sense touch on the glass plate, thus making the tabletop more interesting. You can provide audiovisual feedback as the person's interacting with the tabletop. And we had also designed instrumented objects that are specifically shaped to mimic functional objects. And that's how we are doing more ADL training. And this device was commercialized a few years back as Miro by Tyromotion. So those are the 6 devices that I wanted to talk about. Work that we worked on, but we are not the only people that are doing developing technology like this. There are a lot of other people that are developing accessible and technology with a lot of benefits. And I've shown the pictures of some of these devices which are now commercially available as well. The Grippable, HandyBot, Music Glove, FitMe, Rejoice, Emu. These are all excellent devices that actually fit the bill of providing benefits and being accessible. So that's most of what I wanted to say about accessible technology and some of the work that we're doing. But before I conclude, I'm going to quickly add a few more points as food for thought. See, neuro rehab, as most of us know, is a very complex problem. Unfortunately, the limitations of our devices are also because of the limitations of the field. We are not heavily theory driven, like maybe pharmacological interventions, and that's been a problem. And another issue has been because neuro rehab intervention is quite there's a lot of art to it. We don't really do a good job of documenting some of these processes very well. And in fact, some of the tools that we're developing should be allowing us to do addressing some of these problems. And another important thing to keep in mind: each of these tools is a small component in neuro rehab. They're not the solution. They're a solution, a small part of a solution for the complex problem. And these tools need to be able to do these things very well. They need to allow us to do good documentation of therapy so that we can keep track of what works and what does not. And if we have to make them accessible, a comprehensive evaluation of these tools in different settings is going to be essential. And some of the benefits that we expect from technology might not happen unless and until you have at least a minimum amount of technology. Just having one robot is not going to change your efficiency. Maybe having a few of them for different purposes might be needed. And another thing we also need to do is to, I think, improve the awareness and understanding of what these technologies are and what they can and cannot do. So that's most of what I wanted to say. So in conclusion, most advanced technologies that we currently have are not actually high-value solutions. They have poor accessibility as of now. But there is an increasing trend towards simplifying them and going beyond the clinic, which can address some of those issues. Some of the new tools we design must align with the increasing efforts towards more theory-driven and well-documented neuro rehab. And I think some of the tools that we're developing need to help with this process in routine practice. And I think there is also a need for a lot of multidisciplinary education and understanding, both from the engineering side and the clinical side. And as it was pointed out earlier, co-development, co-design approach is absolutely vital to be able to develop high-value solutions or solutions that have high benefits and high accessibility. That's all I wanted to say. I'm going to stop here. I'm probably taken a little longer than I expected. And thank you for listening. I'll stop here.
Thank you, Siva sir. That was really insightful. If anyone has questions or suggestions, or want to discuss something, they could please write on the chat box before going into the panel discussion and the question and answer session. We have Anshul with us, Anshul Bharadwaj.